In 1991, Pierre Gilles de Gennes got his Nobel Prize for showing that the things he learned and applied to simple matter could be applied to more complex forms of matter. In a way, he got his Nobel Prize for applying what our TED Talks are about: learn, relearn, unlearn. He was especially interested in liquid crystals and polymers. We can see a beautiful picture of a liquid crystal up on the screen, and it has these beautiful colors and the light and the dark regions because it polarizes light. Maybe you don't know it, but you're looking at liquid crystals all day. The pixels in your screens have a little liquid crystal behind them. And the way this works is that the liquid crystal forms this twisted state where the molecules on top, these long molecules, are aligned in a way, but as you go down, they turn around, they twist around. So at the back of your screen, there is a polarizer, and it polarizes light in a way, and then these liquid crystal molecules guide this polarized light to turn the polarization angle around. So by the time it gets to the front of your screen, and there is another polarizer, a horizontal polarizer, it will have turned, and now it can pass through the other polarizer, and your pixel is bright. The moment you want to turn the pixel dark, you have to apply an electric field to that liquid crystal. It straightens out all the molecules, and now the light is not going to be turned around, and it cannot pass through the second polarizer, so your pixel is dark. I know you're going to say, well, I went to EMAG, and they are selling LED TVs. Why are you talking about LCDs? They are also LCDs. It's just a marketing ploy. The only difference between the two is the light at the back is provided by LEDs. A system that de Gennes mentioned in his Nobel acceptance talk is a simple rubber. Now, why rubber is interesting is because it teaches us about a very important characteristic of a soft matter. You have a tiny change at the molecular level or at the microscopic level, which leads to a big change at the macroscopic level. When the tree sap flows from the tree, it's a liquid. But once it gets to the air, it becomes solid, it becomes rubbery, elastic. You can use it for rubber. And this is because links are formed. This liquid consists of long molecules. This is a polymer system, and they can flow next to each other. But once they form links, then the whole thing becomes elastic. Now, they worked a lot to make rubber useful, and actually it took many, many years and many, many trials for Mr. Charles Goodyear to figure out what you have to do. You have to actually heat up rubber in the presence of sulfur to induce even more links, and then we get the rubber that we can use today. At science fairs, if you've been to science fairs, and I guess this is the crowd that has been to many science fairs, one of the interesting soft matter systems that you can see is cornstarch mixed with water. Cornstarch mixed with water is very interesting because if you move your hands slowly, it will feel like a liquid. If you punch it, then it will feel like a solid. If you run through the whole thing like this gentleman does, hopefully you don't slow down and don't sink, then it acts as a solid. Why it does that is because the cornstarch is little particles. It doesn't mix atomically. It has these colloidal particles. When you hit it, the water gets squished out from between these particles, and they form arches and bridges, and they can support the weight of a person. Such a material can be used, for example, in viscoelastic coupling, in four-wheel drive vehicles, and the newest thing that was proposed is to use it as a liquid armor. We already have Kevlar to protect soldiers. Now, if you impermeate Kevlar with this kind of liquid, this shear thickening liquid that we talked about, not exactly cornstarch, but something similar, what happens is when the soldier moves leisurely, that is slow motion, so then it's going to flow like a liquid. When the bullet hits, it is a punch, so it's going to stiffen up and help to make a smaller entry puncture because it's going to spread all this pressure around. You have seen also probably beautiful soap bubbles, and it's amazing. Nowadays they can make surfactants that make these soap bubbles huge, and they are really beautiful. And they are also, the surfactants are a soft matter system. And these surfactants are appropriate to talk about because this is how Dejean ended his talk. He quoted from Boudin. He quoted these verses: "Have fun on sea and land. Unhappy it is to become famous. Riches, honors, false glitters of this world. All is but soap bubbles." Pun intended, because he was working in soft matter, so he wanted to show everyone that soft matter is all around you. The way soap works is that it's a long molecule. It has a head that likes the water and a tail that doesn't like the water. It likes grease or oil. This is why you can wash your hands with it. This is how the soap bubble is formed. You can see the thin layer of water, and then the soap molecules are on each side with their heads liking the water towards the inside. Okay, now if you take the soap molecule and you take molecules that are like the soap molecule, make a layer out of them, actually make 2 layers out of them, and combine them together, what you get is a lipid bilayer. These are very important in biology because they form the membranes of your cells. So in a certain way, you are all but soap bubbles. If you take this material, if you take this material and make spheres out of it, what we can use these spheres for is to encapsulate some kind of material inside, for example, a drug. In chemotherapy, you want to deliver toxins, but you want to deliver these toxins exactly to the tumor site. It's much better to have these toxins encapsulated, travel around in the body, find the tumor, and get accumulated in the tumor site, and then be activated in the tumor site, poisoning hopefully only the tumor and not the rest of the body. You can see the obvious advantages over this so-called targeted drug delivery over the classical way of just poisoning the whole body and hoping that the patient doesn't die first. Soap bubbles, all these soap bubbles. So let's go back. Why do soap bubbles have so beautiful color? So you have the light hitting on the top surface, and there is this other guy, the other light wave hitting the bottom surface and coming out. So the guy that had to go to the bottom had to do an extra waving. Now when they come out, they can wave together. In this case, you see the color, and if they wave the opposite wave, then you don't see the color. This is why, depending on the soap film's thickness, you can see colors in the soap bubble. If you make materials, such as colloidal crystals, regular arrangement of these little spheres that are on the size of the light wave's wavelength, then what you get is a very interesting interaction with light. You can see this in nature, in opal crystals, beautiful opal crystals, in the peafowl's feather, in the color of the butterfly, and we can also make them technologically. We can mimic this. We can create systems that have sizes on the order of the wavelength of light. If we make a one-dimensional system, well, I'm sure there are cameras around because all I see are the lights, but they all have this anti-reflective coating on them. Now if you make a two-dimensional system, and for example, we can get optical cables that are better at transmitting information called photonic crystal fibers. An interesting example where we can learn from nature is the moth's eye. The moth has incredible night vision. It's because it's living in the dark. It really, really doesn't want any light to be reflected off of its eye. All the light should go in. Even the little light that it can get at night, it should go in. So we can learn from this structure, build a similar structure for solar panels to not lose light, but capture it all and convert it to electricity. And then if we make a three-dimensional colloidal crystal, which is going to interact with light, it is a possibility to make optical transistors, light controlling how the other light can pass through or not. This is analog to the electronic transistor, so it would enable us to create a wholly optical computer. Whether this is feasible and is going to compete with electronic computers is not yet clear. These are only prototypes. Okay, so we talked about how we can have colloidal crystals that interact interestingly with light. And the question is, can we do it the other way around? Can we act upon these little blobs of colloids with light? Can we push them with light? So actually, light has a pressure, and believe me, if you would be on this stage, you would almost feel this pressure. But I am quite big compared to a colloid, and I don't get pushed to the back of the stage. But if I would be a colloid, if I would be a micron size, I would be pushed by all this light. And this is what Arthur Ashkin did. He pushed colloids with light. And what he saw is that they not only get pushed, but they get trapped by this laser light, where the laser light is more intensive. You can see it in this picture. If you're not in the most intensive spot, there is more laser light going from the right to the left, so you're going to get pushed as a colloidal particle from the left to the right. So, all in all, the colloidal particle will end up in the focus of the laser light. So now we have tweezers, optical tweezers, to move these little things around. So we have a playground, and scientists love nothing more than a playground to play with. You could see beautiful molecular sets outside at the expo. What you can do with colloids, you can do these toy systems 1,000 times smaller. So these things will behave like the atoms, with the huge added advantage that you can see them through a microscope. So the first thing that a scientist does is, of course, play around with them. And what I do is computer simulations of these systems, giving suggestions to the experimentalist, and then the experimentalist giving suggestions to me. And the first time I actually put my hand on a holographic optical tweezer was at Yale University at Eric Dufresne's lab, where he let me play with one of these. This is a brave man letting a theoretical physicist touch his equipment. Well, I only touched the keyboard, so he was fine. One of his work, you can see it here, it's the, well, you can't, well, I don't know if you can. It's written out the word lux, because Yale University has this biblical motto, lux et veritas, light and truth. And how fitting it is for the optical tweezers. They shine light to see the truth about these little guys, how they move around, how they behave. So what I suggested is a simple way of moving a lot of these colloidal particles from one side to the other. The way you do it is you put it on a piezo stage, the whole system moves, and meanwhile this whole system is moving, you're shining the light on top of them. You're switching the light on and off. If you do this at the right time, what will happen is that the light will act like a little broom. It will broom all the colloidal particles, it will swipe all the colloidal particles from one side to the other. And on that bottom, yeah, you can't see it, trust me, the little particles go from the left to the right. Random things are happening. All right, so playground. So people played on this playground. Arjun Yacht Group at University of Pennsylvania studied how a material melts, and you can actually see how it melts. There is a deformity in the material, a grain boundary, and that's where the whole melting starts. Another researcher, Persinidis from University of Brown, Alexandros Persinidis, he worked on how a defect site moves in a crystal, and we explained it theoretically. Me and my collaborators from Los Alamos National Laboratory, Charles Reichardt and Cynthia Reichardt, we studied this same system with computer simulations, and we showed how this system moves around. So basically the defect picks a direction and it's going to walk in the same direction until it gets into a state where it's like, maybe I go into another direction, and then it goes in the other direction, which you can see here. Another experimental group that I visited was the group of Clemens Beckinger. You can see their beautiful setup in the center. This whole thing is tiny. You would think after all these pictures it's big. No, it's micron size. And what they are doing is these colloidal, one of their experiments that I would like to talk about is these colloidal quasicrystals. Quasicrystals, or Penrose tiling, they're interesting because they have a fivefold symmetry, and related to that is that you can make very slippery contacts if you can manufacture this on the atomic level. You would all think that we are playing around with these systems. Well, there is more to that. With these kind of optical tweezers and colloids, you can do little pumps, microfluidic or nanofluidic pumps, where you can pump liquid around, and this is very important for systems that are labs on a chip. So instead of taking a blood sample, taking it to the lab, you just put it on this little chip and it does all the analysis for you. And I'm sure those in the medical profession can agree with me that this is a very important step in medicine. So to summarize, I gave you 3 examples of how soft matter should be or could be interesting to you in the future, how it could impact your life in the future. One was targeted drug delivery, which was a biomedical application. A more technological side, there were the photonic bandgap materials, the improved optical crystals, or the MOTS eye that helps us collect light for solar panels. And then I showed you a colloidal playground, which is very interesting for us because of basic science questions, but also it has the promise of delivering super slippery contacts or systems of labs on a chip. There are other soft matter systems, such as active matter systems, where particles push themselves around, or granular systems where you don't have the liquid. I don't have time to talk about them, but trust me, they are very cool systems too. And I would like to give you just one lesson from the soft matter. A change on a very small level can affect the whole system on a big level. So I invite you, with the poet, to see the world in a grain of sand, to be brave to learn, unlearn, and relearn how it actually works, and have fun while you're doing it, like that kid. Thank you.